Hello, my name is Pascal Domichli. I'm working at Transvalor for more than 10 years now in the development department. And for 4 years, I have the pleasure to be in charge of the DigiMu software. The topic of my talk today is to give you an overview of the roadmap concerning the microstructure prediction solution, DigiMu. During metal forming or heat treatments, several microstructural phenomena can take place. They are in general interconnected. Hardening, recovery, phase transformation and precipitations, grain growth or grain boundary migration in general, and recrystallization. In the scope of numerical simulations, they are often neglected, at least partially, because they are not easy to take into consideration. However, microstructure evolutions are of primary importance to obtain good predictions. Actually, microstructure evolutions are even the key point, which is linking the process parameters to the part performance. Better microstructural predictions and control means better parts quality. In terms of modeling, you can consider the microstructure at different scales. Mean field models at the scale of the part describe the microstructure using only mean values. You can find them in the user routine module of Forge and also plug your own mean field model there if you want. Population models describe the microstructure as a population of grains. Each grain is described by some scalars. You can find one in the Dynamics user interface in Forge or use the Dynamics user interface to plug your own one. In full field models like DigiMu, you describe geometrically the grains in the polycrystal in a mesh. The deeper you go in the modeling scales, the more physical description and modeling you can obtain. You can then enlarge the range of validity of your model and obtain more comprehensive results. The price to pay is an increased CPU and storage cost. In this roadmap, I will concentrate my talk on the full field scale modeling with DigiMu solution only. The very first version of the industrial software was released in 2016, and in 2018, the first version with recrystallization was available. The subjects of the first part of my talk will be the content of the actual version DigiMu 4, released in 2020, with a few examples to underline its efficiency in an industrial context. Then I will present the major features of DigiMu 5, which is planned to be released in 2022, non-homogeneous grain boundary energies and precipitates evolutions. Finally, I will give an overview of DigiMu Next 1 planned for 2024 and of its major breakthroughs, which are the incorporation of the new Transvalor user interface and the switch to a brand new grain boundary tracking algorithm that will generate major speedups. Let's start with the actual commercial release DigiMu 4, and let me explain why I think that this version has really taken the full field simulation from an academic context to an industrial context. Let's summarize the main features of DigiMu 4. 3D simulations are now available. This feature is rather dedicated for advanced academic studies and less for the industry. Indeed, we have shown that today the accuracy cost ratio of the prediction is better in 2D. Concerning more industrial features, we have several convenient tools that have been developed. You can analyze in a few clicks grain size distribution in one zone using Fiji macros. You can also plot easily grain size distribution histograms and even animate them. Finally, the models used for the prediction are now opened in a user routine module. You can use it to adapt the hardening law, the recovery law, the nucleation law to your specific needs, or even try to implement your own mean field model directly in DigiMu to check the results obtained in a full field context. During the last years, we have intensified and widened our academic collaborations. For example, Mondragon University has worked on the development of an automated microstructure testing machine. The PhD student June could provide us numerous accurate EBSD data of the microstructural evolution of Inconel 625 in controlled conditions. We could use them to generate a corresponding DGMU material file, and our collaboration will go on to test this material file on real industrial processes. The collaboration will also go on identification for other alloys. Another example is our collaboration with the Advanced Forming Research Center in Glasgow for about 4 years now. They performed a lot of semi-industrial tests on Inconel 718 with temperature and force acquisition and consensus microscopical analysis of the results. They also worked actively on the development of reliable digital twins. It helped us a lot to test and refine our Inconel 718 material file in different complex configurations with or without delta phase. This collaboration goes on with a new DGMU PhD student at AFRC since October 2021 in a project including new British industrial partners. The Institute for Metal Forming, the IBF in Aachen University, has also identified its own material parameters for Inconel 718 in DGMU using an alternative experimental method. They tested it on real industrial cogging process and obtained very encouraging results from the core to the edge of the part. The goal is now to go further and try to improve even more this material file. In parallel, a new project with a dedicated PhD student on steel recrystallization should start soon, including new German industrial partners. Today, more and more companies are using DGMU or use service provision from Transvalor. We have performed various material identifications of nickel-based alloys or steels in the austenitic domain. These identifications were based on various types of experimental data, EBSD, optical microscopy, sometimes only existing GMAC models. I would also like to present you a configuration where DGMU was only used as an intermediary tool to train a neural network model. Sometimes you have to perform a high number of simulations with only a few parameters varying between each simulations, and you only need some quite simple scalar parameters as results. For example, the mean grain size only. In this case, you can try to train a neural network with DGMU simulations to generate the database. For example, here, a heat treatment was modeled by a simple neural network with 2 inputs and 1 output, the mean grain size. The training was done on a database of about 30 DGMU simulations only, and this model allowed an efficient process optimization with instantaneous microstructure evolutions predictions. After this first part, I hope that you are now convinced of the pertinence of DGMU for your company, and I will go further by explaining how we plan to go deeper in the microstructure modeling in version 5. A grain boundary is a large disorientation between 2 crystals in the microstructure. Its energy can in general be considered as constant for a given material and a given temperature. However, if you want to go deeper in the details, grain boundaries energy depend on several crystallographic data. Low angle boundaries, less than 15 degrees, are nowadays neglected in DGMU, but they actually have a non-zero energy, which is growing with the angle of disorientation. They are often called subgrain boundaries, and their migration is of first interest to model continuous dynamic recrystallization. Also, some specific high-angle boundaries can have very low energies, as coherent twin boundaries, for example. They are also neglected in the actual commercial version of DigiMu. As you can see in the image there, with a given misorientation associated to a given orientation of the boundary plane, it can lead to kind of mirror boundaries. There, in spite of the high misorientation, the atomic disorder is low, leading to a low boundary energy. DigiMu5 will allow to compute non-homogeneous grain boundaries. A lower energy boundary will tend to reduce less its length in comparison to higher energy boundaries. This leads, for example, to modified equilibrium angles, as you can see here on the test, at the triple junction. The low angle boundaries are pulling less the triple junction than the classical boundaries. We will take advantage of this feature to try to propose first integrated continuous recrystallization modeling. The second major new feature of DigiMu5 is concerning the modeling of precipitates and oxides. It is well known that second phase particles have a major effect on grain boundary migration by pinning the interfaces and slowing down or even stopping grain growth. This is the so-called Smith-Venner pinning effect. It is then obvious that the evolution of the precipitation state during a heat treatment or a forging process will have a major effect on grain size evolutions. It may even be the cause of abnormal grain growth. In the new version, it will be possible to implement some phenomenological evolution laws for the precipitates. In this example, during the simulated heat treatment, precipitates are progressively dissolving, and then progressively they release the pinned grain boundaries, letting the grain growth. Here, at the opposite, particles precipitate during the simulation and pin more the boundaries. We also hope to be able to describe more in details in this version the coupling between the precipitation state and the recrystallization. Let's move now to the last part of this presentation concerning DigiMu NXT1. This version is planned to be released in 2024, and it may seem to be a very, very long-term perspective for you. However, I want to spend some time talking about it because this version will be a huge breakthrough for the full-field microstructural simulations, both for the academic and the industrial world. First, we will switch to the new Transvalor user interface as the other Transvalor solutions. If you are a front user, you will be able to quickly switch to DigiMu in a very short adaptation time. No more need to learn a special user interface for DigiMu. And furthermore, you will be able to work in a more pleasant and more convenient interface with better integrated tools for the setup and for the results analysis. But this is not the main breakthrough for the NXT1 version in DigiMu. In this version, we will change the core of DigiMu solution. We will switch our grain boundary tracking algorithm and the whole code structure, which is strongly depending on it. Actually, we define the grain boundaries in DigiMu using level set functions. Those are basically distance function, positive in the grain and negative outside the grain. This method is generic, robust, both in 2D and in 3D, and this method can be adapted to a wide range of physical phenomenon modeling. In terms of CPU cost, thanks to the optimization performed in the last years, the accuracy cost was close to the best comparable full-field solutions in the academic world. Now, a new Lagrangian tracking method coupled with mesh adaptation has been developed. This method and the code structure or fully dedicated to grain size evolutions modeling. It is robust in 2D, but not yet adapted to 3D simulations. In terms of versatility, the last studies have shown that it was able to model all the phenomena modeled in DGMU5, even using a simpler way. This method provides incomparable accuracy-cost ratios and outdoes totally the competition of the academic 2D full-field simulation world. For example, here, a huge grain growth simulation with more than 500,000 grains has been performed. It is close to a world record. With the actual formalism of the software, such a computation will be very, very long, quite unreachable. But with the new formalism, it has been performed in only 31 hours on one single core. And if you are using parallel computing, it has been performed in 40 minutes. You can see here the initial microstructure with 3 chain zooms for you to be able to distinguish the grains and the initial polycrystal. Here you can see a multipass hot forging simulation with 4 blows. The first one with horizontal compression, second one with vertical compression, third one with horizontal compression, fourth one with vertical compression, and then maintained at high temperature. The simulation has taken 22 minutes with the new Lagrangian formalism versus approximately 4 hours and 30 minutes with the level set formalism. You can now better understand my enthusiasm and see that the word breakthrough was not misemployed when I speak about this DGMU NXT1 version. Before to conclude, I just wanted also to emphasize that the features present in the commercial version of DGMU come directly from the research done at CEMEF in the metallurgy, microstructure, and rheology group. To give you an idea of the work done in the previous 15 years, you can look on this graph, and every rectangle is a PhD or a postdoctoral study. I also want to underline that this research is mainly funded by the industry with a wide consortium of renowned French companies. And I want to thank them not only for the fundings, but also for their collaboration, because they do help a lot to make from DGMU a software which is really dedicated for industrial use. If you are interested to become a part of this dynamic group for numerical or experimental research work, I invite you to contact Marc Bernacchi or Nathalie Bozzolo. To conclude my talk, I can say that we have widened our academic collaborations in the last years. And if you want to hear more about that, I encourage you to listen to the talk of Olga Bilia from AFRC. I can also say that we gain experience with the identification procedure. Once again, if you're interested, please listen to the presentation of Iman Emrani Alawi, who worked with us at Transvalor for 1 year. Finally, I can also affirm that Transvalor has also gained experience in real industrial processes simulations. And if you want to learn more about this, please follow the presentation of Kitran Nguyen from Safran Tech. Concerning the roadmap of the DGMU solution, the actual version is already well suited for industrial simulation on steels in the austenitic domain or for nickel alloys. You can expect from the next version, DGMU5, to go further in your predictions by taking into account new physical phenomena. And just be patient to let us the time to release the DGMU NXT1 version with revolutionary speedups. Finally, I have the pleasure also to inform you that our development team in Transvalor is growing with the arrival of Karen Alvarado. Transvalor will then also widen its area of expertise and be able to help you even more concerning the experimental characterization and the microscopy. So do not hesitate to contact us for software testing or for service provision concerning microstructure simulations or microstructure evolution problematics in general. Thank you very much for your attention.